Hey, Honors Chemistry. I wanted to make a helpful video to remind us of something that we learned recently and how we could come up with a new SI unit to relate atoms to mass eventually. So first things first, how about we start with water, right? And we should all know the formula for water is H2O. And I'm going to actually draw a particle diagram of water so you can see how I'm counting things. So I'm going to make a big circle for oxygen, and I'll make these two little circles for hydrogen. Alright, so hydrogen, bigger circles, oxygen. Okay, now we could just simply look at this one molecule of water, right? And how do I know it's a molecule? Let's go back to our particle definition. We could either have atoms or molecules. I know this is a molecule because there's more than one color, now it's more than one size. So a molecule is two or more atoms, okay? So here's our one molecule of water, okay? And you might want to write down on the side somewhere that a molecule has two or more atoms in there. If I want to count, I know in this one molecule of water, there are two atoms of H, right? I can see that this is hydrogen, and one atom of O. All right, and that's going to combine in a constant ratio according to Dalton. Dalton said that all matter combines in simplest whole number ratios. So if I need water, I need two atoms of H for every one atom of O. Okay, but as you may have heard or can recall, it's very difficult to isolate one of these molecules. And I could get a canister or a vial like we did this past week or so, and I could have a bunch of molecules of water in here. I don't know how, let's say I don't know how many are in here. Okay, but at the same pressure, volume, and temperature, I should have the same number of particles. Okay, so this was Avogadro who said that. Avogadro said, I don't know how many are in here, but I know that if I have same pressure, same volume, and same temperature, I should have the same number of particles. So if this was water, and then let's say this was another canister that had some other compound in here, or some other element actually in here. Let's call it element X. If it's the same pressure, the same volume, and the same temperature, they should have the same number of particles. The only thing that would be different about them is their mass. Okay? So, just to recap on Avogadro's hypothesis about this same number of particles. Now, it wasn't until a bit time later that this number of particles for a constant pressure and volume and temperature actually had a number. And this number was 6.022 times 10 to the 23rd. I'm going to call it things. Okay? And we could call this capital N little a. All right? And we call this Avogadro's number. Now, he wasn't the one who invented or created this number. It was just honored in his name because he was the one that came up with this idea that there were a certain number of particles in a container. And so what this says is if I have 6.022 times 10 to the 23rd atoms, I'm going to call that 1 mole of atoms. Right? So this is our new unit, right? We call it the mole. So 1 mole of anything, 1 mole of anything is equal to 6.022 times 10 to the 23rd things, or anythings. And I could use any word here. If I have 6.022 times 10 to the 23rd molecules, I have 1 mole of molecules. All right, so this was our new number to represent the number of things. So we had to relate how many atoms or molecules there are to Avogadro's number because it was a number that was constant for all this matter. So if I have, let's use water for our example. If I have 6.022 times 10 to the 23rd molecules of water, I know automatically that that is equal to 1 mole of water. But the technique or the method that's involved with this is doing a bit of dimensional analysis. So we set up a relationship here. My relationship becomes this, right? Molecules to moles is multiplying or dividing, actually dividing by Avogadro's number. So, sorry, 1 mole of water over 6.022 times 10 to the 23rd molecules of water. Okay? And now, notice that whenever I do this dimensional analysis business, the units that I'm given, right, these are my units given, not the number. This units given needs to be in the denominator. It's got to be canceled out. The units given is in the bottom. So pretty much to set up a template for this, it'd be quantity 1 times relationship, and that's between quantity 1 and quantity 2, is equal to quantity 2. Okay? And this relationship has to have a relationship between quantity 1 and quantity 2. So if the question over here would have been, how many moles are in 6.022 times 10 to the 23rd molecules of water, I would divide by Avogadro's number or multiply by a relationship that relates moles to molecules. All right, so if I had a different number, let's say, and I'm going to use a number that's going to give me something that's a bit ugly, and that's okay though. So let's say I only had 500 molecules of water. I want to multiply by that a relationship, and I want to know how many moles there are. So let's say I'm going from molecules to moles, right? I want to go from molecules to moles. I know that molecules of water needs to go in the denominator. And I want moles, so I need moles of water in the top. And the only relationship that relates number of molecules to number of moles is this Avogadro's relationship, or Avogadro's number. 1 mole of water would be 6.022 times 10 to the 23rd molecules of water. Notice how I set that up. I did not put these numbers in first. I put the units in first. And then I figured out the numbers later with a given relationship. And I'm going to do another example like this later. So now something to remember, and I've said this many times in class, if I multiply a number times a fraction, and how do I know this is a fraction? This fraction has a line. So there's a line separating two numbers. So if I multiply my number times a fraction, I multiply by the numerator. Don't forget that. And then some of you might already be mouthing that I divide by the denominator. Okay? So in this problem, I'm going to be multiplying 500 times 1 and then dividing by 6.022 times 10 to the 23rd. So be careful in your calculator. You should always use parentheses. So 500 times 1. I'll do that first. I'll do 500 times 1. That's 500. And that could have been obvious, but I'm still showing you what you could do. You could hit enter. I could do 500 times 1. And then I want to divide by 6.022 times 10 to the 23rd. So divided by left parentheses 6.022 times 10 raised to the 23rd. Right parentheses, and I don't know if you can see it, but left parentheses 6.022 times 10 raised to the 23rd, right parentheses. And if we could guess if this number is going to be big or small, well, if 1 mole is this number, if 1 mole is 6.022 times 10 to the 23rd, if I only have 500, this number should be freaking small. So if I hit enter, I do get a freaking small number, 8.30288941. E to the minus 22nd. Now, don't forget what E means. E means times 10 raised to the. I'm going to simplify this with just 4 sig figs. So 8.303. 8.303. All right, don't forget E means times 10 to the. E means 10 raised to whatever exponent. Okay, so times 10. Times 10 raised to the minus 22nd. And what unit do I want here? Well, my molecules of water canceled out. I'm left with moles of water. And convince yourself that this number makes sense. It looks ugly, but I only had 500 molecules. That is a lot less than 6.022 times 10 to the 23rd, so I should have a lot less moles. Let me do another example. Let me use a bigger number now. Let's say I had 5.25 times 10 to the 25th molecules of water. And I want to go from molecules to moles. I want to end up with moles of water. Okay, I want to end up with moles of water. What's my relationship again? Now, I know that I want molecules of water in my denominator here. I want that unit to cancel out. And again, what is the only relationship right now that relates molecules of water to moles? 1 mole of H2O is equal to 6.022 times 10 to the 23rd molecules of H2O. Now my molecules is on the bottom. I want moles, so I put moles on top. And now I just put in the numbers that relate to that quantity, right? A mole is 1. And it doesn't matter. I'm putting 1.0, but it doesn't matter. You could put 1. And then my molecules is 6.022 times 10 to the 23rd. And now again, on the calculator or mathematically, you multiply by the numerator, which is multiplying by 1, and then you divide by the denominator. So basically I'm going to take this number and divide it by Avogadro's number. Now in looking at this number is definitely larger than Avogadro's number. How do I know that? The 10 to the 25th is a larger exponent than 10 to the 23rd. So I may have somewhere in the hundreds or thousands of moles. So let's see if I get this number. So I'll do 5.25 times 10 raised to the 25th. And I like to, if ever there's like an instance where we have like scientific notation, before I do any math with it, I like to hit enter so it already puts it into the calculator. And then I multiply that times 1, right? Of course I get that back. So just in case this wasn't 1, let's say it was another number. I multiply it by 1, I'll get a number. Then I want to divide using parentheses. So I want to divide by Avogadro's number. 6.022 times 10 raised to the 23rd. And I get 87.18033.876. So I'll just use 4 sig figs. 87.18. And I know that this answer needs to be in moles, so that's how many moles there are. And convince yourself that that makes sense because I have a lot more molecules in this number than I do for Avogadro's number. Now, what if, and the last thing I'll end with here, what if I wanted atoms of hydrogen or moles of hydrogen in H2O? We have to be careful here. Because if I have one molecule of H2O, I have 2 atoms of H, right? And convince yourself that that makes sense, right? If we go back to our particle diagram, if I have one molecule of H2O, I have 2 individual atoms of H. You could use those words interchangeably because an atom is part of a molecule, okay? All right, so for every one molecule of H2O, I have 2 atoms of H. If I had 1 mole of H2O, I would have 2 moles of H, right? So that relationship is consistent. I have a 1-to-2 ratio, right? And just so we're not confused where this comes from, I like to do an analogy. If I had 12 H2O molecules, how many hydrogen atoms would I have? Well, there's twice as much H in a molecule of H2O. So if I have 12 H2O, I would have 24 atoms of H, right? That's still a 1-to-2 ratio. But what if I called it a dozen, right? We know that 12 is equal to 1 dozen, right? So still going along with my analogy here, if I had 12 H2O molecules, how many dozen is that? Well, that's 1 dozen H2O molecules. If I had 24 atoms of H, how many dozen atoms of H do I have? Well, if you know that 12 is a dozen, 24 must be 2 dozen atoms of H. So this is just an analogy of how you could do that. A mole is a new unit for us. So a mole represents 6.022 times 10 to the 23rd. So if I have a mole of H2O, I should have twice as much H, or twice as many moles of H in H2O, because that little 2. There's 2 H's for every H2O. So I'm going to need this relationship if I want to figure out H. So let me go back to this number here, right? We had 500 molecules of water. So let's say I have atoms or molecules to moles. Okay? Let's say I had 500 molecules of H2O, and I want to know how many moles, or let's say I want to know how many moles of H there are, right? So I want to go from molecules to moles of H atoms. Okay? Now we have to be careful. I want moles of H over here. All right, so later on, I'm going to need something that ends up with moles of H. Okay? Now, there are 2 ways to do this, but I'm going to do it this way. Molecules of H2O, right? I know that I want molecules of H2O in the bottom. What can I convert or relate molecules of H2O to? Well, there's 2 ways of doing this. I could relate molecules of H2O to atoms of H, or I could do what we did before, and I could relate molecules of H2O to moles. Let's do that. Let's be consistent and say 1 mole of H2O is 6.022 times 10 to the 23rd molecules of H2O. I know that for sure is a relationship. Again, if I have a mole of H2O, I have 6.022 times 10 to the 23rd molecules of H2O. So I'm going to put that here. These units are going to cancel out, and I'm going to be left with a unit of moles of H2O. But I don't want moles of H2O. I want moles of H. So if I have moles of H2O here, I know I got to put moles of H2O on the bottom here, right? I want these units to cancel out. Now, in order for that to happen, I need some other relationship that relates moles of H2O to moles of H. And guess what? I have that right here. 1 mole of H2O is related to 2 moles of H. So I'm going to use those numbers here. 2 moles of H for every 1 mole of H2O. So now if I do this math, you do 500 times 1 divided by Avogadro's number, right? You multiply by the numerator, divide by the denominator. And then you multiply by the numerator again and divide by the denominator. So basically it's going to be 500 times 1 divided by Avogadro's number times 2 divided by 1. Okay? So let me do that. I'll do 500 times 1 divided by parentheses 6.022 times 10 raised to the 23rd. Do not forget parentheses. It's so important, right? Divided by 6.022 times 10 to the 23rd. And then I want to multiply this by 2 and divide by 1, which is the same thing. And I get 1.66 times 10 to the minus 21st. And how does this number compare to the number on the other side? Well, this number is 8.303 times 10 to the minus 22nd. And this number is 1.66 times 10 to the minus 21st. This number appears to be twice as much as the number I got for water. And that makes sense because I should have twice as many hydrogens as I do for my molecules of water. Okay? So convince yourself on how to do this type of math and relationships between atoms and molecules. Just like as a heads up, let's say I was going to go backwards. I'll do that last example. Let's say I was going from moles to atoms. Let's say I have backwards now. Let's say I had 36 moles of H, right? So I have moles of H to maybe, let's say I wanted to go to molecules of water. Okay? So if I have 36 moles of H, I can convert that to either atoms, or I can convert that to relating that to molecules or moles of water, right? In the end, I want molecules of water. And so as far as units need to cancel out, I know I want molecules of water on top here, and I know I want moles of H on the bottom here. So I could relate moles of H to water, right? I know that for every 1 mole of H2O, there are 2 moles of H. So 2 moles of H, 1 mole of H2O. And these two units will cancel out. And I'll be left with moles of H2O. And now to go from moles to molecules, you'll see that I want mole in the bottom, mole of H2O. And I want molecules on top. And the only relationship that relates moles to molecules is, again, our Avogadro's number. 1 mole of H2O is 6.022 times 10 to the 23rd. So I could do 6.022 times 10 to the 23rd over 1 mole. And so if I do this math, I'll do 36 times 1 divided by 2 times Avogadro's number divided by 1, and I'll get my answer. So I'll do 36 times 1 divided by 2, so I get 18, and then I'll do 18 times Avogadro's number. And don't forget to do parentheses. 6.022 times 10 raised to the 23rd. And I get 8 times 10 to the 25th molecules of H2O. And this number is larger than Avogadro's number because I definitely had more than a mole here. Okay, I had more than a mole to begin with, and I'll have more than a mole of water. Okay, so just like a summary, if I want to go from atoms to moles, I'm most likely going to be multiplying by this ratio, 1 mole over 6.022 times 10 to the 23rd atoms. If I want to go from moles to atoms, I want to multiply by Avogadro's number over 1 mole. Okay? And be careful, the only other thing that I did not put down here is that when you have relationships between atoms or moles in a molecule, you have to multiply by that relationship, right? So again, that quickly recap, if I had moles of H and in the end I wanted something with water, I have to relate my H to water. And I use the compound, I use the chemical compound or the chemical formula to figure that out. Okay? So, I'm hoping this very long video was very helpful for the first practice set that asks you to relate moles to atoms and atoms to moles. If you have any questions or concerns, please let me know. You could comment on the video or you could message me in the remind.